Today, what we'd like to do is look at an application of Newton's second law to a physical system that is extraordinarily common, very useful. You might think of it as a special application. It really isn't. I'm not going to do anything differently than I would applying Newton's second law to any other problem. I'll need free body diagrams and I'll write Newton's second law. But we're interested today in the particular case of an object moving in circular motion. So I've drawn here a circle, and here I have the object at the top of the circle moving with a velocity that I'll call v1. That velocity has a magnitude that is the object's speed. And what I'm going to do for the moment is I'm going to consider that the object moves around the circle with constant speed. That's not a requirement, but it does simplify the analysis at first here. So it goes around at constant speed. It'll take a certain amount of time to go around once, commonly known as the time period. And also it'll go around in a certain number of times in a given time interval, say the number of cycles per second, which is known commonly as the frequency. So if I'm going to let this thing move around at constant speed, and it starts here with a velocity v1, sometime later I'll draw it further along the circle. It will have subtended an arc length s here along, and I'll draw it again here. Now when I draw the velocity in this position, that velocity will be tangent to the circle at that point, because the velocity vector is always tangent, but the magnitude of that velocity vector is still the same. That is, v1 and v2 have the same magnitude. So I can describe the motion from position 1 to position 2 in terms of a speed. All I would have to do is measure the amount of distance traveled along that arc and measure the amount of time it takes to traverse that distance and divide, and I would get the magnitude of the velocity vector that is the speed. But there's another way that I can describe that displacement from one location on the arc to another, and that is with the angle subtended. You'll see here I've drawn in, associated with this arc length, the angle theta that is subtended in that amount of time. And so I can describe the position either way by the arc length or the angle subtended. What I choose to do here is to describe very quickly a mathematical relationship that doesn't really have much to do with physics, but is a fantastic utility, not only in our classical mechanics, but going forward also in our electricity and magnetism. And that is the arc length formula. There is a simple relationship between the length of the arc and the angle theta, and that is that the arc length is equal to the radius multiplied by the angle. I have to be careful, though, but for this very, very powerful and useful equation to be true, I cannot measure the angle in degrees. I have to instead measure it according to a new angle measure, and here's how it works. Imagine that instead of going just a short distance along the arc length here, that I went all the way around. Everyone knows that the distance that I will have traveled is the circumference of the circle, is 2 pi times the radius. So the arc length would be 2 pi r is equal to r times theta. You see these r's cancel, and I find that when I've subtended the entire arc of the circle, I've subtended an angle that must be equal to 2 pi, where pi is 3.14 and some more digits. Clearly, 360 degrees is not the answer. This is the reason why we have radian measure. Radian measure exists so that this equation, this extraordinarily useful equation, is true. And so therefore we say that there are 2 pi radians in a circle, and we divide the rest of the angular displacements around the circle up according to that angular measure. So that's just an aside there regarding the math. What my real goal is here is to calculate the acceleration of the object in this uniform circular motion. You might argue, there's no acceleration to calculate because you've said that you're going to have it move along at constant speed. And so as it traverses the circle, it goes no faster or slower as it travels. Well, that's true. But appreciate the fact that the velocity vector changes direction from position 1 to position 2. A change in direction is a change in that vector. My definition for acceleration is that the acceleration vector is equal to the rate of change of the velocity vector, and that change does not simply imply magnitude. Direction does just fine. So I'd like to calculate how much acceleration there is, because if I find the acceleration, I know that Newton's second law certainly applies in this case. I don't need a new set of physical laws for it, but I know that that acceleration will be associated with a force, and I'm quite interested in being able to solve this common problem. So in order to find out what the acceleration is, I'm going to have to somehow compute dv dt, and it's going to require a little bit of cleverness on my part. Let me draw here the velocity vector v1 removed from the diagram. All I have to do to make the equivalent v1 is to draw a vector that is horizontal and has the same magnitude as v1 drawn on my diagram. It's rather tricky to do. It might be easier for you in your notebook, but here it is, v1 laid down on the board. I'm now going to draw v2 in a very strategic way. I'll pick up v2 from where it's drawn on my diagram and I'll move it over so that the two vectors v1 and v2 are now tail to tail. Maybe a little mysterious as to why I'm doing this, but you'll recall from the introduction to our course that if I have the vectors v1 and v2 drawn such that they're tail to tail, and I draw a vector from the tip of v1 to the tip of v2, that vector is delta v, the change in velocity vector. This is rather obvious because delta v is equal to v1 minus v2 that's not true. It's equal to v2 minus v1, pardon me. It's equal to v2 minus v1 by definition. And so if I add v1 over to the other side of the equation, I get delta v plus v1 is equal to v2, and I swap the order, I find that v1 plus delta v is equal to v2, and my diagram establishes that according to what I understand is my graphical method for adding vectors. So here I have a vector diagram showing the difference between the two vectors delta v, and I know that delta v is related to the differential of velocity dv, just that delta v is large, and dv is an infinitesimal change. So I'm going to take this vector diagram and remove the vectorness from it by replacing the arrows with simply lines. And the reason why I'm doing this is because I want to make the argument that the magnitude of the vector v1 is equal to the magnitude of the vector v2 is equal to the constant speed v with which the object navigates the circular motion. And so I draw my diagram again, same diagram, you see, but it's the arrows are absent. And so I have the velocity, or the speed, pardon me, here, and the speed here, and delta v being the other side of this triangle. The angle interior, which I should have mentioned previously because it conspicuously appears here, you can do some construction lines with this and move the v2 over and find that this angle theta that is subtended by the object along the circular arc as it goes from the first position to the second is the same angle between the two velocity vectors v1 and v2, and so it appears again here in my diagram. Now I'm going to make an extraordinary and inappropriate claim. I'm going to claim that delta v is equal to v times the sine of theta, and you should immediately balk at that, primarily because the triangle that I've drawn here is clearly isosceles and not a right triangle. Trigonometry refers to relationships in right triangles, and this is not a right triangle. But I'm going to ask you to suspend that disbelief, because imagine, what happens if I make the angle smaller and smaller? Here, use your imagination to imagine this line here closing, 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 making the angle smaller and smaller and smaller. As I do that, the triangle, the isosceles triangle, becomes more and more of a very, very narrow wedge. As you look at it, just as you look at it aesthetically, you might be able to make an argument to yourself that that looks more like a right triangle than my original triangle does. We say it can look like a right triangle as much as you like. It is not exactly a right triangle. And I say, yes, that may be true, but consider this. For any right triangle, the hypotenuse is longer than the adjacent side. But the smaller the angle interior to that right triangle, the smaller the angle, the closer the magnitude of the hypotenuse comes to the magnitude of the adjacent side. In fact, if that angle were to be infinitesimally small, say an angle d theta, then the length of the hypotenuse and the adjacent side become exactly equal to each other. It's in a sense the thinnest right triangle you could possibly imagine. In that case, of course, I'm not getting a large change delta v on the far side here, but an infinitesimal change in the velocity dv, and that's excellent because I wanted to know dv in order to compute the acceleration. So this is the direction that I'm taking in my proof here. So imagine that I start here with a change in velocity delta v equal to v sine theta. That was my argument. An approximation that we will commonly make in our physics going forward, we'll take advantage of this, that if the angle is very, very small, then the sine of theta in radians, the angle in radians now, that's a requirement of some of the arguments that I'm making here. The sine of theta is approximately equal to theta. This is called the small angle approximation. So if I make that small angle approximation, then delta v is equal to v times theta. Well, I'm going to make my delta v very, very small by making the angle very, very small. I'm going to trade delta v for dv and I'm going to trade theta for d theta. And so my relationship becomes that dv is equal to v times delta v. It's nice having dv, but I didn't want dv, I wanted dv dt. Notice my definition of acceleration is a vector definition, but I've lost my vectorness here in favor of the magnitudes. That's okay. I'll get that vector direction at the end of the argument. But what I want is dv dt, and so I'll divide both sides here by dt such that dv dt is equal to v delta or d theta dt. Well, now I've exchanged one problem for the other. I wanted to know what is dv dt, and now I find myself asking the question, what is d theta dt? Well, that's okay, because perhaps I can calculate d theta dt because I know a little bit about the angle. My arc length formula says that the arc length is equal to the radius times theta. So let me solve that equation for theta, and right here that theta is s divided by r, the arc length divided by the radius. Once I've done that, I can now take the derivative of both sides of the equation with respect to time, such that d theta dt on the left-hand side is the derivative with respect to time of s over r. Now, this is circular motion, and circular motion implies that the radius is constant. That's how I define a circle. And so the radius does not change as a function of time, and so it comes out of the derivative. So d theta dt is 1 over r ds dt. Well, ds dt I know. The rate of change of the arc length with respect to time is equal to the rate of change of position as a function of time is the speed. And so what I find here is that d theta dt is the speed divided by the radius. And so now I can fully construct the derivative of the velocity with respect to time as the derivative of the speed with respect to time, which is the magnitude of the velocity in this case, as v times v over r, or v squared over r, and that is the magnitude of the acceleration. There's still a little bit of work, a little bit of argument to make to get the full vector, but that's the magnitude of the acceleration. This vector, this acceleration is called the centripetal acceleration. And it's called centripetal acceleration because of the direction that it points. Let's return to this little differential diagram that I have here, where d theta is becoming quite small indeed, and I have a thin wedge of a triangle with a little differential dv there. The direction of dv in this diagram, I'll add a little dotted line to it and a vector that points downward. The direction of that dv, as d theta becomes smaller and smaller and smaller, becomes ever more perpendicular to the direction of v1, and is therefore pointing always in the direction perpendicular to v. But as the object goes around in circular motion, v is always tangent. So if the velocity vector is always tangent to the circular motion, and the acceleration vector, which is of course proportional to the dv vector, must ever be perpendicular to the velocity vector, then that means that the acceleration vector that I'm seeking points radially toward the center of circular motion always. The acceleration vector points radially towards the center of circular motion always. It is an acceleration that seeks the center, and that's the Latin derivation of the term centripetal, to seek the center. So yes, I have the magnitude of the acceleration. It's the speed squared divided by the radius, and now I know the direction of that acceleration, because in the case of uniform circular motion, that acceleration is ever drawn toward the center of circular motion. Now that I know that acceleration, I've verified that one exists because I can calculate how much acceleration there is. When an object goes around in a circle at constant speed, I would probably seek for the force that causes that acceleration, because I know that it's the natural tendency of objects to persevere in their motion, and with no force acting on it, an object will not travel in a circle, but will in fact go off in a straight line forever and ever. So since I can tell from v1 and v2 that the motion is altered, I'd like to know what is the force that is the cause of that motion. When I look to real physical systems, I'm always going to look into it and find a force that is the cause. It can be any force that I know of. It can be the force of gravity. It can be a normal force, a friction force. It can be the force exerted by a spring. It can be electric forces, magnetic forces. Any one of the forces could cause alteration of motion, but when it does, it'll have to obey Newton's second law. And Newton's second law, cast in with regard to circular motion, would be the sum of all the forces that act radially, either toward or away from the center of circular motion. The sum of all of those forces is equal to the mass times the acceleration. But now I know that the magnitude of the acceleration is v squared divided by r. So I can have this relationship between forces and acceleration exactly as Newton's second law predicts. So I haven't invented new physics here. I've simply applied Newton's second law to the case of uniform circular motion. But I had said right at the beginning that the motion need not be uniform. I could have a situation where an object follows the circular path around, but that its speed changes, increasing or decreasing as it makes that trip around. The reason why this would happen is consider here that I have, again, a circular trajectory that this object, once again drawn at the top, is going to follow. But now the object is subject to a force. It's at a peculiar angle. Here I just draw the force down at a sort of arbitrary angle directed to the right. This force is not pointing radially towards the center of the circle. I might say that it is not a centripetal force. It is not a force that points entirely to the center. But I can describe it in the context of two components. I can always divide any vector up into its components. And so I'll divide the force up into a component that I call Ft, which is directed tangent. It is the tangential force. It is that component of force that causes the object to speed up. In this case, I've drawn it in such a way that it would cause the object to speed up. To speed up in the circular trajectory as it goes. There is another component that I'll label Fr, directed radially towards the center of circular motion. And it is that component of force, or combination of those components of force, that are responsible for the circular motion. And so since there are two components of force in non-uniform circular motion, then there are two components of acceleration. And I should appreciate that the total acceleration of the motion is calculated this way. Since there are two components in our two coordinate directions of circular motion, radial and tangential, then the total acceleration is equal to the square root of the sum of the squares of those components. Be careful here. Be careful because I'm talking about components in a coordinate system where one coordinate direction is radially towards the center. That direction changes continuously during the motion. So when I'm making this description, I am describing a non-inertial reference frame. Indeed, even if the object goes around in circular motion at constant speed, is this motion with constant acceleration? No, because the magnitude of the acceleration vector remains the same, but the direction of the acceleration vector changes continuously. 3 essential problems applying this new idea of centripetal acceleration. What I'm going to do, and this is, we need names for all these essentials. I guess I'm going to call this the vertical loop. Somewhat nostalgic, I think, for some folks in the audience. The vertical loop is sort of a roller coaster thing. What I'm going to do is have a loop, like it's an amusement park ride. Not wild about how I drew that. And the idea here is that I have some sort of like roller coaster car, and it's going to come in here with some velocity, and it's going to execute this loop. As it does, my everyday knowledge of this, the velocity is going to change. It's going to slow on the way up, and it's going to speed on the way down. I'm going to ask you to suspend that for a moment and just imagine that there's some way that I executed at constant velocity. Or constant speed, pardon me. I don't need it to go around at constant speed, but it's not the issue that it speeds up or slows down. I'm going to comment on it anyway. I'm going to draw free body diagrams in order to understand the motion. I'm going to draw free body diagrams at 3 locations. When the car is here at the bottom of the loop, again, when it's here sort of in the 3 o'clock position, draw a free body diagram for that, and then a free body diagram when it's at the top of the loop and is essentially inverted. Those 3 positions I'm interested in, and I'm going to draw free body diagrams for all 3. So let me start. I'll draw the free body diagram for the bottom down here, and then for the side over here, and then for the top up here. You know what? What I'm going to do for convenience is I'm going to draw the forces directly on the cart. I don't like drawing my free body diagram on my diagram, but just for the compactness of space and the ease of doing it. So here the cart sits at the bottom of the loop. And I know that it has weight, so I'm going to draw that weight vector, label it mg, directed straight downward, because that's the direction the weight acts always. And in its motion through the loop, there's nothing about the loop is going to change the nature of the force of gravity. So I won't have to overthink it. The weight force is always downward. The cart sits on a track which is directly beneath it, so there's a force of contact, and that contact is perpendicular to the track and directed upward. That is the normal force. And so there is some normal force directed upward. I guess I should have, these vectors should be sort of the same magnitude. They're not the same magnitude, actually. The weight should be shorter, but there you go. There's the normal force and the weight directed downward, and that's the free body diagram for the cart in that position. Now, at the 3 o'clock position, the weight of the cart is still directed downward. So there it is, mg directed downward, and that is the cause of the slowing that would take place as the car ascends. There's a weight force directed downward, so there's a vertical component of acceleration. It's reducing the component of the cart's velocity that is upward. And the cart is in contact with the track still, but the track is to the right of the cart. And so the normal force there is going to point radially towards the center of the circular motion, perpendicular to the track. And so we see as the car ascends, its free body diagram changes. The situation is quite complex because as it goes from the bottom position to the 3 o'clock position, its free body diagram changes continuously through that entire motion. When it gets to the top, now I have an even stranger situation because, of course, the weight force, mg, is directed downward, and the normal force is also directed downward. So the free body diagram changes as it goes around. And since the free body diagram changes, how I apply Newton's second law to it changes. So let me apply Newton's second law to the bottom first, and I'll write the sum of the forces here at the bottom. The sum of all of the forces that act radially is equal to the mass times the speed squared divided by the radius. I've discovered that in circular motion, the component of the acceleration directed radially towards the center of circular motion has a magnitude of v squared over r.
So we're just going to say the friction doesn't matter?
Oh yes, I'm neglecting friction in the problem. That's certainly true. The friction would be, because the friction is along the surfaces in contact, the friction would be tangential to the motion all the way around. So although the friction certainly would affect the dynamics, it does not affect the radial equations. So even if I had added friction to my free body diagram, it wouldn't appear in any of these radial Newton's second law. So the sum of the forces acting radially for the bottom free body diagram is going to be equal to the force, the normal force directed towards the center as a vector, plus the weight force directed radially away. There is a convention in solving circular motion problems. It's absolutely critical that toward the center of circular motion is chosen as the positive direction. Towards the center of circular motion is chosen as the positive direction because the centripetal acceleration is assumed positive directed toward the center. And so at the bottom position here, the normal force is positive and the weight is negative. So the normal force minus mg is equal to mv squared divided by r. Notice that the normal force, just a little comment I'll make here, that the normal force is not equal to the weight here. A conclusion that I draw from this, as I can just solve by adding mg to the other side, is that at the bottom the normal force is equal to mv squared over r plus mg. There are a common mistake made here is a student will see this situation and say, oh, the normal force is up, the weight is down, the normal force is equal to the weight. No, the normal force is not equal to the weight in this case because it is accelerated motion. The normal force is equal to mv squared over r plus mg. And that makes sense because what does the normal force have to do in this situation? It has to provide for the circular motion and plus support the weight. It has two jobs. It has to do both of those jobs. Provide the circular motion, the force that is the cause of the centripetal acceleration, and still support the weight. In the 3 o'clock position, the situation is much simpler. Because if I'm going to calculate or to write a Newton's second law for the sum of the forces that act radially, there's only one such force in the 3 o'clock position. It is the normal force directed radially towards the center of circular motion. It is the normal force directed radially. The weight will not appear in this equation because it is tangential. Now, it does have an effect. It's creating a tangential acceleration, but I don't care. What I care about is the radial forces. In this case, that radial force is simply the normal force, and so the normal force is equal to mv squared over r. A way that I can say that, a way of talking about that, is to say that in the 3 o'clock position, all the normal force has to do is provide for the circular motion. It no longer has to support any of the weight of the cart. Its only job in the 3 o'clock position is to cause the circular motion. I'm interested in the free body diagram at the top particularly because the top is where all of the fun happens, it's where all the action happens, and it's where all the death starts to happen. And so I'm interested in my analysis at the top of the circle. At the top of the circle, I'll write once again the sum of all of the forces that act in the radial direction is equal to, well, here I have the normal force and the weight, and they both point downward. They are not negative forces because they point radially towards the center of circular motion, which is the positive direction, and therefore they are positive forces. So it is the normal force plus mg, which is equal to mv squared over r. A little analysis similar to what I did at the bottom of the loop. If I solve for the normal force would be mv squared over r minus mg. And the story that that equation tells is that the normal force has to cause the circular motion at the top, except to the extent that the weight helps. See, at the top, the weight is doing some of the work to provide for the circular motion. And so the normal force doesn't have to push so hard to cause the circular motion because the weight is helping. Now imagine that I go through this loop at a very, very high speed. I go around and execute the loop and come out the other side and everything's fine. But as I go slower and slower and slower and slower, eventually things get scarier and scarier and scarier at the top as I go slowly through the top, and will I make it? And then come through. There is a critical speed at which I negotiate the top of the loop and I just make it without losing contact with the track. And because I have this equation now, I can derive that particular velocity. That critical velocity, if I'm less than that velocity, then I'll lose contact with the track and become a projectile. Well, that's no good. If I go faster than that velocity, I negotiate the loop without any trouble at all. So let's figure out what that is. The velocity at which you lose contact. Well, the normal force is the force of contact. So losing contact means the normal force must become equal to zero. Indeed, as I go slower and slower and slower through the loop, the normal force gets smaller and smaller and smaller until eventually the normal force becomes equal to zero. The consequence of that is that mg is equal to mv squared over r. The m's cancel, and I can solve that for the critical speed. The critical speed of executing the loop is the square root of g times the radius of the loop. That is a classic result of physics, and in an introductory course of physics like this one, it comes up in homework and on exams very frequently. And so it should be a familiar result, which is really the primary reason why I'm calling it essential in this context. Two more. I'd like to consider now a fun amusement park ride called the gravitron. So the way that the gravitron works is that you have this circular room, and the circular room has some radius, and the folk go inside of it. I don't like the way my diagram is. The folk go inside the room, and then they stand against the wall, and the room rotates with a certain velocity, and then what they find is that you feel like you're being pushed to the outside, like you're being pressed against the wall. And in the older version of the thing, I don't think it happens on the newer versions of this ride, but back in the day, the floor of the ride would fall out, and then you'd be stuck to the wall with no floor below you, and that would give you a sense of alarm. But of course, if the physics is done right, you stick to the wall just fine, and you don't fall out of the bottom of the ride, unless something goes horribly wrong. And let's imagine that it works appropriately. In order to analyze this motion, and maybe I'm building the thing, and I want to understand with what velocity do I have to turn the ride so that the people stick to the walls. Oh, by the way, and so you feel like you're being thrown to the outside, like you're being pressed against the wall, but that's just your natural tendency. But the wall is pushing you towards the center. So in an action-reaction sort of way, you feel that you're being thrown to the outside. That's fictitious, because in your mind you're applying Newton's second law on a reference frame that is accelerating. And that's a no-no in terms of interpreting the forces that are acting. Okay? All right. So in order to analyze this, I'll need a free body diagram. So I'm drawing a free body diagram for the person and the forces that act on them. Certainly, the person has weight, and so I draw the weight vector mg directed downward. And the person's back is in contact with the wall, and so that wall force is a normal force that points radially towards the center of the ride. And I immediately realize that is probably the force that is the cause of the circular motion. But I have a question now. Why don't I just fall out of the bottom of the ride? I mean, the idea is for me not to fall out. So there must be some force that is causing me to not fall out. And that force would have to be directed upward in opposition to gravity, and we soon realize that that is in fact the friction force directed upward that prevents me from falling out the bottom of the ride. So applying Newton's second law to the gravitron, the sum of the forces directed radially towards the center of the circular motion is equal to the mass times the speed squared divided by the radius. The force pointed towards the center of circular motion is the normal force. So the normal force is equal to the mass times the speed squared divided by the radius. And it was my goal to determine what speed should I run the ride at. But I can't know that unless I know the normal force. So I need something a little extra to complete the analysis. So I'll write the sum of all of the forces along the y-axis is equal to the mass times the acceleration along the y-axis. To get more information, I'll write another Newton's second law equation because I have a whole coordinate direction I've ignored. Taking upward to be the positive direction, the friction force minus the weight mg would have to be equal to the mass times the vertical acceleration. The mass times the vertical acceleration. Well, the vertical acceleration is 0, which means that the friction force directed upward is equal to the mass. Well, I went through some trouble in the last lecture to describe the friction force in a general sort of way as being the coefficient of friction mu times the normal force, which then would be equal to mg. Well, there's my normal force that I need in the context of how frictiony or how frictive the walls of the ride are. So I can write this as mg divided by mu and make a substitution. So I go back again to my initial version of this. So I have mv squared over r, which is equal to the normal force, but the normal force is mg divided by mu, apparently. And so you see now the m's cancel in my algebra, and I can come to the conclusion that I sought, which I'll just write down here. The conclusion that I was looking for, just solving for the velocity. Notice that that velocity is equal to the square root of gr divided by mu. It's a little amusing that it looks very similar to the previous result of the vertical loop, but with just a little bit of mu thrown into it. And so that's the speed that the ride must go around in order to provide for the circular motion. Now, my hope is to do another example of it, and I have the time to do it. So, another example of circular motion, the banked curve. You'll find, if you examine closely, roads going around curves, particularly highways, are not flat, but they in fact bank to the inside. And the reason for this is that if I choose the banking of the curve properly, it's possible to create a curve that at a particular speed, the curve can be negotiated without any friction, providing for the circular motion. So I'd like to do the analysis of that and see what happens. Here, I'll make an inclined plane sort of thing, but you have to appreciate that what we're doing is we're looking at the road like a cross-section of the road. I draw a car on this road, which I lament because the car that I draw on the road always looks terrible. It just looks like some sort of psychopathic beaver or something. And I haven't figured out a way to draw it so it doesn't look ridiculous, but there it is. And it's got the antenna on the back. I don't know, there it is. I don't know what... I have to spend some time alone practicing. This car is coming towards you. It's coming towards you. It will exit the board, and it will enter the board over here. So I'm going to put in the angle theta right here. This is the angle of the incline. I would like to analyze this motion. I'm going to analyze it in such a way that I'm claiming that it's going with a particular speed. It does not require any friction to make the turn. That's the free body diagram I'm going to draw. So I'll draw my free body diagram here, and you want to resist the urge to draw the inclined plane free body diagram, because that's not, I don't want the car to slide down to the inside of the radius. I don't want the car to slide outward to the outside of the radius. I want it to negotiate the banked curve at a constant radius. So acceleration up and down the incline is not only not the issue, it's undesirable. So when I draw my weight vector vertically, I'm totally content with that, mg, because the weight vector has no component that's directed radially towards the center of circular motion. So it's not of issue in terms of helping the car to negotiate the turn. However, the normal force directed perpendicular to the incline does have a component directed radially toward the center of circular motion. That component is n sine theta. You can look at the arrangement of the angle there, draw some vertical lines through it, some registration lines, and discover that the way the angle is with relative to the normal force, that it's the sine component of the normal force that points radially towards the center. I'll be honest with you and say that for my purposes in physics, that is a thing that I have just memorized. I simply know that in this very classic essential example of physics, that it is the sine component of the normal force that is directed radially towards the center. So the sine component directed radially towards the center means that this component directed vertically must be the cosine component of that normal force. So when I write Newton's second law for the radial direction, the sum of all the forces that act radially is equal to the mass times the speed squared divided by the radius. Well, this means that n times the sine of theta, which is the only force that points radially towards the center of circular motion, must be equal to mv squared over r. And I sort of have the same problem here that I did in the gravitron problem, that I don't know what the normal force is. I don't know how much normal force there is in any given situation or in any particular speed. And so I write Newton's second law for the vertical direction as well. Well, drawing it for the vertical direction, you see, it is a force equilibrium situation, because the car, when it goes around in circular motion, is not accelerating vertically. It's only accelerating radially. So I'll write that n cosine theta must be equal to mg. So here I have n times the cosine of theta is equal to m times g. And I have a similar problem, that the unknown normal force appears in my equations, causing me a little consternation. Well, I'm going to do a little trick here that's very, very helpful when you're doing naughty algebra sometimes. I'm going to take the equation, simply divide the equations. It's probably something that you haven't done before, but I'll divide them, and when I do, the normal forces cancel. The masses cancel. And you see what I have as a result is sine theta divided by cosine theta, which is of course the tangent of theta, which would be equal to the speed squared divided by gr. I've simply taken v squared over r and divided it again by g. Now I can solve for the speed, and I find for this essential that the speed is the square root of gr times the tangent of theta. And that is the critical speed that I can negotiate this curve without friction.